So this is the fourth lecture, right? And what they used to do during the Saas Bhi Kabhi Bahu Thi, when they will go through several episodes, then they will do a recap episode. They call it Maha episode. We'll not do Maha episode. We will do a recap itself. So yeah, in 3 lectures, what did we learn? Did we learn anything? Okay, let's see what did we learn. And I want people to participate. And you know, when you go through the list, you find the people starting with name A first, right? So we are going into a little bit of astrophysics now. Yes. All those 3 lectures were on astronomy. And we will start with the that happens. I'm going to cut the ribbon and we're going to talk about the sun. Right? This is our local star. People say that this is an ordinary star, garden variety of star that you can find in any garden. Right? But this gives a very great lesson to us that a person could be ordinary, but still he or she could be everything for somebody. We live because of that. Our sun could be very, very small, negligible compared to many more stars. It may not be as exotic as neutron star. It may not be as gravitating as the black holes, but it is sufficient to energize our whole solar planet, sustain the life, give us the energy for everyday work and so on. Right? So this is our star, real star. There could be millions of trillions of stars, but for us, he's everything. He's our universe. So in this lecture, we are going to learn 2 things. Actually, I decided to first tell you this about the stars and the sun, but then I finally decided to talk about sun first because some things will be covered here. So we'll discuss first the structure and composition of sun, and then what are the sources of sunshine, why it shines so bright. Some parameters. The mean distance, you know this, AU was designed to measure the distance between Earth and Sun. It was given a name of one astronomer. Mass of the Sun, huge, 10 to the power 30 kg. Kg is missing. Diameter, 1.3 into 10 power 6 kilometers. I'm sorry for that. I'm not writing those units, right? I'm getting infected by some of you. Mean density, 1400 kg per meter cube. If you want to know, if you want to compare it with something else, what it should be? Take it water. What is the density of water? Yeah, 1
gram per centimeter. 1000 gram per centimeter.
Yeah, or 1 kg per liter. A liter is how much? 1 kilogram per liter. And 1 liter is how many meter cubes or centimeter cubes?
1000 cubic centimeters.
1000 cubic centimeters. You can convert that. So it is not too dense, but it is denser than any other thing. You can compare its density with the solids. Right? That's an home assignment for you. You can compare these parameters with Earth's parameter and some other material you know. G is 273. So of course it is more gravity than Earth. Right? This is luminosity, 3.8 into 10 power 26. What is the unit of luminosity? Watts. It is energy radiated per unit area per unit time. Temperature, 6000 Kelvin typically. These are some of the parameters of the sun. Could be good for putting a small section on the poster on the sun. But this took a lot of invention, lot of hard work to know each and every parameter. right? Different kind of techniques you have to develop. Now we know these things. Composition, 73% is hydrogen, 25% is helium, and only 2% is of the other gases, which is carbon, oxygen, nitrogen, neon, magnesium, silicon, then sulfur and iron. So this is the different composition from that of the Earth. We have not discussed that, but it is different from that. Right? In Earth environment, we mostly have nitrogen. Silicon we have, carbon we have, oxygen we have. The thing is that most of the elements are in the form of atoms. Why? Mostly. And because of extreme high temperature, the atoms are not, they're ionized also. Ionized means electrons have been stripped off, right? That means you have charged ions and the electrons, large number of electrons. So there is that's a plasma for you. Under certain additional conditions, it's a collection of charged gas which satisfies certain criteria. Right? So they say that sun is basically, most of the sun is plasma, in the plasma state. Matter on the sun is in the plasma state. And even otherwise also they say that 99% matter in the universe is found in the plasma state. Only 1% is in the solid and gaseous. Solid and gaseous. Right? It is in the plasma state. How do you get the plasma? Simple. You draw that picture. You take a solid, you take ice, give it some heat, it becomes water. You give it more heat, it vaporizes. You give more heat, it will get ionized and so on. So they sometimes, because of that, they sometimes call plasma also to be a fourth state of the matter also. The only difference is that when you go from solid to liquid or liquid to gas, you find a phase transition. But from gas to plasma, you do not see that kind of behavior. Phase transition means there will be some latent heat and those kind of things.
Like, sir, can we say the reason is for like sustaining a plasma state? The plasma state itself, it's just a local equilibrium.
Locally?
Local equilibrium. Like as far as we remove the temperature source, it will try to recombine, right? Which is not the cases with other phase transition. हमने temperature हटा दिया तो भी vapor phase पानी में आ जाए.
Yeah, that could be true. That could be true for some of the system, but not for all the system. That we will discuss. So this is the structure of the sun. After the composition, this is the structure of the sun. You can see there are several layers, right? The innermost layer is they call it core. And then you have radiative zone. Then you have convection zone. Then you have photosphere. Then you have chromosphere. And then you have corona, right? So let us discuss them one by one. This is basically layers of an onion, right? You remove one by one. This find that. So the first thing is core. This is extremely dense, hottest part of the sun, and the source of all the energy we get from sun is radiated by sun. And this is approximately 20% of the solar interior. And what is the temperature? 15 million Kelvin. Huge.
10%, not 10%.
Yeah, 10 power 7. 1.5, 10 power 7. Next comes the radiative zone. As the name also suggests, some radiative processes might be going on. Somebody said something. Yeah, so the radiations are basically all kind of radiations could be, right? We know the electromagnetic radiations. There could be photons visible, there could be infrared, there could be gamma rays, and so on. Right? All kind of radiations could be there. But the reason we call it radiative, because there are three ways in which the heat can transport: conduction, radiation, and convection. So here, whatever heat you have in the core is basically coming out through the radiative processes in the form of radiation.
किस तरह के मतलब किस वेवलेंथ वो एक क्वेश्चन हुआ उसके लिए सर कोड में हम ऐसा स्टेटमेंट दे सकते हैं कि क्योंकि हाइड्रोजन का प्रोपोर्शन ज्यादा है तो उसके ट्रांजिशन लेवल्स पर किस वेवलेंथ पे रेडिएशन होगा वो कह सकते हैं थोड़ा बहुत सर इट विल बी सम नेक्स्ट
No, are you talking about visible radiations also? No. There could be different kind of, there could be nuclear transformation, gamma rays also, X-rays also, visible also. I don't know. Let's not talk about it. We are just trying to understand what are the different layer cause. If you go into detail of everything, that would be too lengthy. Radiative zone we call it because the processes are radiative. Right? You know how the radiation happens. We get the sunlight from sun to the earth. There's no medium. How it travels? It travels through the radiation. Right? That's why we call it radiative. Whatever energy you have in the core, it travels out in the form of radiative processes. You can read about radiative transfer. So high density of matter in this region. So what happens? The density is very, very high. So whatever photons, whatever radiation they are trying to come out, they undergo the collisions. And because of that, they go in the zigzag path. What kind of radiations are there? So are these radiations generated due to nuclear fusion in sun? Yes, we are going to talk about that. We'll discuss what is the reason of sunshine. So frequent collisions. You know the simple example. If you could see the board, I can draw something. This part is visible, I guess, right? So you know how the current flows in a wire conductor. You connect it to battery, plus and minus. So electron will flow from here to here. Let's say this is the electron, and you will get current in this direction, right? But what happens? First of all, there is not one electron only. Had there been only one electron, then this would simply travel from here and reach quickly. And at what speed?
Inverse of this length.
Yeah.
1/6 of speed.
So it will be simply this. The potential energy, that will be EV. This is the voltage given by the battery, equal to half mv square. Right. So this will move so fast, and this will come out to be of the order of 10⁶ meter per second. But that is not the drift velocity we know. What is the drift velocity? Some centimeter per second, few centimeters per second. It moves so slowly. Why it moves so slowly? It undergoes various collisions. It simply does not follow this electric field and gets accelerated. Force equal to Q into E. No. It goes here, it sees so many other electrons. And how many electrons could be there? Equal to the number of density, which is of the order of copper. Solid density is even more. Avogadro number is only for gases at standard temperature and pressure. They are even more dense. So it is definitely more than this 10 to the power 23. Right? So these for solid will be 10 to the power 28. So these many particles in a small region. So it's like that somebody is trying to come out of that crowd. So it will really take, he can run, but he will not be able to run. Because he will go here, he will try to take another path and slowly will come out. So the drift velocity is the effective velocity, which is not 10 to the power 6 meter per second. You can calculate it for, let's say, V equal to 10 volt. You know everything else, right? Electron mass, electron charge. You can calculate. but it is only of centimeter per second. It is because of that collision.
6 हाँ sir अगर 10 ना ले तो भी 10
Right.
or 12 6 or
Right. Same happens with the photons also. They were generated in the core. Now they are trying to come out of that core. And while coming out of the core, they are talking to the other particles. That's why it takes lots of time for them to come out. Right?
going through other particles in the cell, they are undergoing various transitions.
Sorry.
They are becoming responsible for various transitions for other atoms.
Yes. So again, those are the details. Because what is happening that photon might be losing energy, might be creating another photon, and so on. So those are the details of the collisions. Collisions are not simple phenomena to understand. You have to start with the scattering theory, and then take various effects into account, and so on. But had there been no resistance, not so many particles, or if everybody was flowing in the same direction, then resistance would have been very, very small. And consequently, your electricity bill would have been very, very small. Right? So collisions, they will come everywhere. Now, the third layer is basically the convective zone. The name also suggests now the transport of energy or the heat is happening via the convection. What is convection?
Something without contact.
Example, this is how the water boils. This is how the water boils. So what happens? This is the source of heat. This is the source of heat. So particle, they will take this heat and then move up. And particles which are having less kinetic energy or at less temperature, they will come down. You will get a kind of convection current, kind of vortex. That also will happen. Third thing you know, the conduction. Conduction is always happening because there is always some matter in the contact. Conduction कैसे होता है? Yeah, this rod, you start heating from this end. Yeah, and particles are not moving from their position. They are just transferring their energy to the neighboring particle, whatever excessive energy they have. So, see that becomes gradually gets. And what is the fastest way of heat transfer? Radiation, at the speed of light. Ideally, if there are no collisions. Collisions can really bring it down. And then in the convection also you will get when they are going up, you will encounter several other particles. Right? And so on. Right. So these are the three layers. And this is a very big layer. It's 2 lakh kilometers deep. Right? Sun is really a giant star. Compared to other star, it could be ordinary, but it is really a giant star for tiny people like us. Right? Now comes the visible layer. So these layers are not visible. We cannot see these layers. We can only indirectly observe these layers by doing some calculation, by observing some spectrum, by collecting some other data, and so on. But then there are 3 layers which we can really see. And first one is the photosphere. Name also suggests. After this layer, the sun becomes opaque. So we really cannot see the other layers. What are those? The core, and then so before photosphere, the core, radiative zone, and convective zone. And after that, we get photosphere. This we can see. So they are saying that it changes almost perfectly transparent to almost completely opaque. Right? And this is not too big compared to the convective zone. It is only 400 kilometers. And again, the pressure is very, very, very small. It's only 10% of the Earth's pressure, which is 1 atmospheric pressure. How many Pascal it is? 1 atmospheric pressure.
101.325.
And density is also very, very low, right? Very, very low.
Sir,
However, the other core and other, they were very, very dense region, right? But here we have number of particles are very, very small. So it is, these are the regions which are dominated by the radiation, not by the matter. Yes.
Here, because it is said it is very opaque. So either number density has to be very high.
No, it is not opaque. After this, the sun becomes opaque. After photosphere, sun becomes opaque. So you can see all the layers, including photosphere and above it. But you cannot see further to photosphere. Right? These are some of the recent photographs taken of the photosphere. Right? So the photosphere really looks like the granules. Huh?
Very good flower.
Right, very good flower. Now we are really developing lots of optical and advanced telescope, right? You can see, I mean, some millions of kilometers away. This photograph. Now you can imagine the zooming power of your telescope. So the next visible layer comes the chromosphere. This was not known for a long time. Chromosphere. So not visible also. But you can see this chromosphere during the eclipse, moon eclipse. There are most of the light from the sun is blocked. So this becomes visible. Because photosphere is the brightest part. So if you're seeing that, then you will not see anything else. The same as because if you go to a village, you can see lots of stars. But if you come to a city, then because of city light, you will not see any star. Or even the sun also, you don't see any star now because sun is shining so bright. Not seeing same way happens. But if you block that light, photosphere, then you should be able to see the chromosphere. And this is again 2000 to 3,000 kilometers thick and 10,000 Kelvin. And its color is reddish color. And reddish color is basically because of the hydrogen spectrum, dominant line emitted by the hydrogen element, right? And in 1868, they found another element which was totally new. That time it was not known, and that was the helium. So astronomy has also contributed to the periodic table of chemistry. They found this helium, and now we know that hydrogen and helium are there on the sun. We will shortly discuss that they are responsible for most of the energy, including nuclear fusion, as somebody pointed out in the chat. Hydrogen and helium. They reside in the, not they don't reside, but you see those colors in the chromosphere. They are in the core. Core is basically where you have lots of all the substance and material. The sun is a fireball, right? The actual size of the ball could be small, but the flames can make it look very, very big. The biggest part is really the corona. We'll discuss that. So this is the chromosphere. It looks like this red color. Right? If you take all these things out. Finally, the most elusive part of the sun is the corona. People are really trying their head out to understand how it forms, why it is so wide and so on. So this is very, very hot. Temperature is nearly 1,000,000 degrees, which is much, much high compared to the surface of the sun. Right? And this extends from millions of kilometers above the photosphere. Right? It is again very bright. Again, particle density is not too high. It is reasonably okay. 10⁹ atoms per cubic centimeter, which is a very low density matter or plasma. You can call it. But the important thing is this statement. The corona extends so far into space, far past Earth, that here on our planet, we are technically living in the sun's atmosphere. Now imagine, that's the corona. That's why even if the sun is very, very far away from us, it plays a very, very crucial role in the Earth atmosphere also. So this is not that coronavirus, but the name came because of this, because they also have this corona kind of structure around them, like the sun has. Right? So people are really trying to understand what is happening. And another interesting thing is, what should happen to the temperature if you are away from the fireball? Temperature should decrease, right? But here it is totally different. The corona, you had very high temperature at the core, fine, and the surface temperature was low, and then again it started increasing. Corona is very, very hot. You don't know, right? There are several theories and predictions, but no clear-cut answer to it. Especially the widespread of. Somebody wrote something in the chat box. What layer of the sun has plasma? Yeah, all the layers have the plasma. All the layers have plasma. The density may vary, right? So the highest density will be in the core. And when you come out, then density will decrease. So this is the photograph. इसको बोलते हैं coronagraph, they call it. So this is the technique where you basically block the light coming from the photosphere. And you can really see lots of bright. That's the corona, which is spreading, I mean, far, far away from the sun itself. Let's see. Right? The sun is really, really a violent star. This is an interesting plot, which I wanted to show you. As I said that the temperature should come down, but this is not the case. You can see the temperature, and this is the height in the solar atmosphere. So in the core, temperature is this. It goes down, but then it goes up, remains constant, and then increases. There's a transition region also. From chromosphere to corona, there's a transition region where it really very, very sharply increases. And the corona, it goes up to 10 to the power 6 and beyond that. This is what people are trying to understand using various plasma models and other information. Right? Interesting, isn't it? So why is the solar corona is so hot? Why it is taking so much energy with it? So plasma, the question, answer to the question is plasma is everywhere. Right? From here to here. This also has plasma, this also has plasma. This is a big plasma. Photosphere has plasma. I don't have density plot, but that way. Right. Now coming to the very, very interesting phenomena, the solar wind. So what happens, you know, sun is a very, very violent star, and sometime what happens, it loses lots of its mass in the form of highly energetic charged particle. And that phenomena is called as the coronal mass ejection, CME. So these are very, very highly energetic charged particles which travel towards the Earth. And when they reach the Earth, they interact with the Earth's magnetic field, which is very, very weak, but still the charged particles are very, very highly energetic, so they can interact. And then they redistribute the Earth's magnetic field. That is known as the phenomenon known as the magnetic reconnection. And there you see lots of light flashes gets generated. That we call as the aurora borealis. I'll show you this picture. So you can see some of the parameter. What is the speed? They're traveling at the 400 kilometers per second. 1 million miles per hour. Huge. Right? And they are, as I said, they are very, very high. They are highly energetic. So this is the measure of their temperature. So they are very, very hot. Right? And see the number. The sun is losing about 1 to 2 million tons of material each second through the wind. This is nothing compared to the Mars Sun has. Right? I want to play this video for you. How will I do that? Did not generate the link. Yeah. Copy and paste. Is it called plagiarism? I'm not sure for online people whether the sound will play, but let's try.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from?
Here comes the sun. Beautiful video.
This is where the tale of the aurora starts. On the sun, a star of average size among billions of other stars in our Milky Way. The sun acts as an enormous power plant. The energy is created deep inside the core of the sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the sun. In the outer layers, the heat moves to the surface in huge eddies called convection cells. These electrical currents of charged gas create magnetic fields inside the sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band. Then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. After 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Right. This is what I wanted to show you. This is the picture we have, the auroras. So you should sometime visit this place. The sky will look really, really beautiful. see now something is happening on the sun, and those effect of that we are seeing on the Earth. That's lots of plasma physics is there. The phenomena of magnetic reconnection, as I told you, this is a phenomena which basically converts the magnetic energy into kinetic energy. That's how the particle get ejected from the sun's atmosphere, because they are bound to the magnetic field of the sun. But then those magnetic field lines break and they eject the particles, very highly energy particles. And now they again interact with the magnetic field of the Earth. Again, the magnetic reconnection happens. We see these kind of flashes.
Sir, so to generate the field, as it was shown in the video, the whole dipole field was traveling, right, in the space. So that means the super particles, charged particles, must move in a certain way to keep that field. No?
Yeah, that is the dynamic field. It will keep changing also while traveling. But most of it is vacuum. So you can see it is a kind of robust kind of structure which is traveling without altering its shape.
How a charged particle would take the field with it and
no, charged particle can produce a magnetic field, isn't it?
yeah.
Charged particles themselves, moving charged particle, they are current and they produce a magnetic field.
Okay, so that was the reason, like they were showing the magnetic field was traveling.
Right. It's a charged particle which are carrying electric field as well as magnetic field. Right. Now coming to the sources of sunshine, as somebody pointed out. Again, reminding us some of the parameters. It is 93 million miles away. It is very, very old star. 4.5 billion ago seems to be its origin. And this is very, very luminous star. 4 into 10 power 26 watt. People online can hear me all right?
Yes, sir.
Did you get the audio of the video we played?
Yes, sir.
Yes, sir.
Perfect. Right. So now, without going in too much, let me discuss what were the models, earlier model, 1 or 2 models, which were proposed to explain the source of the energy, the sun. The first one was very, very interesting, right? People thought that it could be because there are, what we are getting a heat and visible light, basically radiation. So the source could be anything. It could be mechanical, it could be chemical. People tried all kind of thoughts. They thought chemical also, that some chemical reaction might be happening. Lots of gasoline, all cold kind of material might be burning on the sun and we are getting. But when they do all those calculations, they slowly discard those things. What are sunspots? Okay, sunspots are basically the area from where this mass has been ejected, right? So there you see kind of holes where there's no matter, right? But they again evolve because nearby matter and energy will try to take that place. So those are sunspots are because of that. Right, so people thought that lots of meteorites are falling into the sun. And that is resulting, and that those meteorites are basically converting into they are burning and giving you the energy. Why can't people speak instead of writing? Okay. So, but people thought that if the lots of meteorites are falling, on an average, they did some calculations. But if the meteorites are falling, that means that sun's mass is also increasing. And because sun's mass is increasing, then the gravitational pull will also increase. And that should change the Earth's orbit period by 2 seconds, which is definitely observable. But people did not find any evidence. So they discarded that. Next thing was basically they proposed the conversion of gravitational energy into heat. But again, there was a picture with that problem with that picture. What was it? That will result in the shrinkage of the size of the sun. That was also not observed for long duration. Right? It is not possible for sun to stay hot as bright and shrink in size as well. Right? And with the corona, that really discarded lots of the hypotheses. But finally, the current understanding is that it is the nuclear fusion which is responsible for the energy, the shine, sunshine. What is nuclear fusion? We know from our, maybe we know the nuclear fusion and fission,
Yes.
the two processes. Right. So what is this? Picture A. Fusion, the two light nuclei coming together and forming a heavier nuclei. And the second picture is fission, very heavy nuclei converting into two smaller nuclei. Right?
So practically, like energy has been provided in both of these reactions.
But till they tend to go to the stateless line.
Sorry, but I did not get you.
But the energy is provided to both of these reactions. Fusion
Why?
and fusion.
Why?
Because like sir, मतलब फ्यूजन में ट्रिवियल लगता है कि हम एनर्जी प्रोवाइड करते हैं to fuse two of the nuclei.
So why we give the energy? Why energy is required to make the fusion happen?
It is to fuse two nuclei. It is in orders of magnitude, right?
So
To combine them, we require
fission is simple. You have a heavy nuclei, you can bombard it with the neutrons, it will break, right? Energetic, highly energetic neutron. Remember both the,
Because hydrogen being stable, to make them react with each other to fuse them, you will require some energy.
yeah, because you have to work against the repulsive force.
Yes.
We'll discuss that shortly, right?
repulsive
Here it is
and
basically you can bombard it with the, so you can give some kinetic energy, it will break. That's the simplest picture. But these are not that simple. You have to bring all those quantum mechanical calculations. So, right. Liquid drop and those pictures are not complete pictures. Shell model and liquid drop. You have to really go more advanced pictures. But that is fine. So we will focus on the fusion only. So what happens in the fusion? It is a three-step process. The first step, what you get? Two hydrogen nuclei. Right? Nuclei means all the electrons have been stripped off. So hydrogen has only one electron. So these are the two positive charge. Now you want them to interact with each other. For that you have to apply the force. It is like that when you want to bring the two north poles together. How you can do that? You can only apply the external force. And when you bring them closer and closer, you know the force required will increase because the separation between the magnets is decreasing, and hence the force is increasing. Now you have to apply larger and larger forces. Same will happen with these also. But you have to bring them so closer so that they can interact with each other. And that, I'll say phenomena, not phenomena, that parameter is known as the cross section. If you bring them close to that, within that cross section, then the nuclear fusion reaction will happen. You don't have to bring them infinitesimally close. You don't have to make them touch each other.
up till a certain length.
Right. So for that, you need to apply energy because you have to bring the two positively charged nuclei close to interact. So what happens here? You get a deuteron and a positron and a new particle, which is neutrino. So this was not known initially. Later it was discovered. Because how it was discovered? Because people found that the total energy should be within these two particles, which are expected to generate, positron and the deuteron. But when they calculated this energy, the total energy came out to be smaller than the expected. Right? So people thought that there could be different regions. Finally, they thought that they predicted that there could be another particle which is taking that energy, and this could be massless, undetectable, moving very, very fast, and so on. And that's how the neutron was hypothesized and finally discovered.
Also, like the kinetic energy of the particles involved in the products, they were assumed to have fixed finite values.
Right. So conservation of energy. It's energy before the reaction, energy after the reaction.
It was a distribution.
Right.
So that
right? So in the second stage, you got this deuteron and hydrogen atom. Now they will fuse to give you a helium isotope. Sorry, what did I do? And a gamma ray. So all those things are supposed to be happening in the core itself, right? So this is the radiation you are getting coming out. And then finally, the hydrogen, the helium isotopes, they will fuse to give you a helium nucleus and then the two more hydrogen atoms. So hydrogen is getting converted into helium, helium is giving you hydrogen atom. So this is the nuclear fusion process. And all these reactions are exothermic reactions. They release lots of energy, right? In terms of radiation, in terms of kinetic energy. There are only two ways possible, right? Getting energy with either h nu or it is with the particle, the rest mass plus the kinetic energy. So to understand these calculations, you also need to bring out the special relativity because the particles are moving very, very fast. Their kinetic energies are comparable to their rest mass energy. You have to bring those calculations into. And then quantum mechanics, of course, you have to apply. Eventually, you have to do the relativistic quantum mechanics. I don't want to. And that will be your last course on quantum field theory. So these processes, they do not look like the two particles interacting. They will be dealt in some different way in the field theory, right? Where the interaction will be understood as the exchange of a particle. This is interesting. Somebody wrote something in the chat box. In stars other than the sun. Yes. Yes. In other stars also, there are only two processes which are very, very dominant. The nuclear fusion, which gives the radiation pressure, and then the gravitational force. But the important thing, can we have, so people ask this question, that sun has so much energy. Can we make our own sun? Can we make sun in the laboratory? For that, people wanted to do the nuclear fusion. But that nuclear fusion should be controlled nuclear fusion, right? Otherwise, everything will be destroyed. So they call controlled. So people tried several schemes.
Artificial.
Yeah, artificial sun they call it. The most successful scheme is the tokamak,
Yes.
which is a fusion machine, fusion device, which is the kind of torus, which looks like a rubber cycle tube. ITER, yes. So this is a picture of ITER. So 7 countries, they have come out to collaborate. Yeah, it is an engineering challenge, right? They call it International Thermonuclear Experimental Reactor, ITER. This is really, really big. So you can see this is a person sitting there. From here, you can imagine the size of this machine. Right, this is the torus device. There's a cross section of that. It's a kind of cycle tube. So plasma is formed within this. Now coming to your question, yes. Coming to your question, you asked that plasma will not remain sustained. That depends upon, because you know this plasma is charged particle. The moment they strike any material, they will get absorbed. Well, you can say they will get recombined. So they will not remain positive and negative charge. So what are the ways? You need to confine them. You need to confine them such that they do not touch anything. So they move around each here and there, but without touching any wall. Because if they touch the wall, they will decombine. That phenomena is known as the confinement. The current challenge is that you need to confine it for longer time.
And it can't be using just walls. It has to be using magnetic field.
In the sun, yeah. So in the sun, you get a natural control. What is the natural control?
Convection.
Sun's own gravity.
Acha.
So that gives the confinement to those plasma particles. They do not leave the sun. They remain confined there. Right? Yeah, gravity. But here on Earth, the magnetic field is the answer. Why? Because we know that the charged particles, they follow the magnetic field lines. So can we design a magnetic field in such a way, round and round, so that particles follow those magnetic field lines and they do not diffuse, they do not leave those lines. And because they will not diffuse, they will not travel outside those field lines and will not strike the walls and hence will not recombine. Yeah, so this is the scheme that people are trying to develop. Yes, so sun's confinement is known as the inertial confinement. Inertia means it's sun's inertia, or the gravity, which basically gives you the confinement. So this is known as the magnetic confinement. So you need three things. You need to confine plasma for long duration so that the nuclear fusion processes can happen. Why you need to make them plasma? Because that increases the cross section, reaction cross section. If you make the hydrogen nuclei to interact as a particle, that cross section will be very, very small. So you want to make them in the plasma state. Right? Now you have to confine the plasma. The plasma should be confined for long duration. Plasma should be very, very hot. And plasma should be very, very dense. So these three parameters. Right. So I think Janvi has gone through this course on plasma physics, maybe. Yeah. Yeah. So laser confinement fusion, that is also a variant of inertial confinement fusion. So we need three things. Yeah. So we need N, P, and tau. This should be greater than 10 to the power 23. This is known as the Lawson criteria. So N is the density, T is the temperature, and tau is the confinement time. Confinement time. Right? It should be product of these should be. But the problem is, if you increase this, then you will lose on this. Because now you have more and more particles. To confine them, you need higher and higher magnetic field. And design of that magnetic field is also not very, very easy. You need to design a very, very powerful superconducting coil to generate that kind of magnetic field. Yeah, sort of. So that you should not be missing the magnetic field line. Because your ideal magnetic field line should be this. They should not be crossing each other, right? Then only particles. But if there are distortion in the magnetic field line because of whatever instability or any kind of irregularity, then confinement will not be perfect. Right? And again, if you increase the temperature, then diffusion will also be large. If you control one parameter, you lose on another parameter. So it is a challenge, physics and engineering both. But if we get this, we will get a clean energy and enormous energy. Right? This seems to be the solution for now, maybe for another century. Let's see. So we have another video here. Sure. So this I'll play again. This is not that good, but okay to understand. It's not as good as the one we saw.
You might not know what SSL is, but hackers do, and they hate it.
We also hate it.
During nuclear fusion, two nuclei fuse while releasing energy. The fusion of deuterium and tritium nuclei is best suited to produce fusion energy. Deuterium consists of a proton and a neutron, while tritium contains a proton and two neutrons. During the reaction, deuterium and tritium nuclei collide, producing one helium nucleus and one neutron, and releasing energy. As the positively charged protons from the nuclei repel each other, high activation energy is necessary for the atoms to achieve sufficient proximity to each other and start fusing. When the reaction takes place, more energy is released than invested. The reaction is exothermic. When nuclear fusion takes place in stars,
The activation energy is provided by the enormous pressure and energy of gravity. The devastating force of the hydrogen bomb is also caused by nuclear fusion. The energy necessary for the fusion in a hydrogen bomb is provided by the explosion of a nuclear bomb. A peaceful use of fusion energy has not yet been developed. Several reactors have been built, but their operation is not economical. It requires more energy than it releases. However, the technology offers great promise. Deuterium and tritium are available in basically unlimited amounts. The operation is environmentally friendly, as the end product is helium. There is no radioactive radiation, and a huge amount of energy can be obtained from a small amount of fuel. A large international project currently underway will probably result in a breakthrough in developing nuclear fusion. The construction of the International Thermonuclear Experimental Reactor, or ITER, began in 2006 in southern France. The reaction itself takes place in deuterium-tritium plasma, that is, ionized gas consisting of electrons released by the atoms and of deuterium and tritium nuclei. The activation energy is provided by heating the plasma to a temperature of about 100 million degrees centigrade. At this temperature, the wall of the reactor would melt. Therefore, the plasma is kept in motion in a ring-shaped magnetic field. The magnetic field is produced by a toroidal electromagnet. This type of fusion reactor is called a tokamak reactor. The plasma in the tokamak is heated by electricity and microwaves. The fusion reaction starts at an extremely high temperature. The construction of the ITER reactor is expected to be completed by 2018. It has been designed to produce 500 megawatts of output power or 50 megawatts of input power for up to 100 seconds. The ITER has been designed for developing and testing the necessary technologies for energy production, not for industrial energy production itself. Another reactor, the 2000 megawatt demo, has been proposed for continuous energy production. The 7 participants in the ITER project are the EU, the US, Japan, South Korea, India, China, and Russia. The full cost of the project is about 16 billion euros, half of which is paid by the EU. This international collaboration will hopefully result in an environmentally friendly and safe technology for continuously satisfying increasing energy demands.
You know, what
No,
makes
we
me
don't.
really, really sad?
I'm sorry for that. So we really should go ad free, right? Right. So time to stop here. Can you tell me what is this? Parker probe.
Yes.
So this is a recent probe sent in, it's flight in 2020, I guess. 19. And now it will be collecting. It is expected to give us more information, more understanding of this sun. This will really go very, very close to this sun. Right. Parker. So it was again, he was a great solar astrophysicist. He gave this model of reconnection of a sweet Parker. So time for questions.
So the plasma was moving like in a spiral way through the torus, or just they were
The
like
electrons move like spiral.
so the fields are like the fields are set up like that. It should move in a torus path or
Around the
in a spiral way.
No, fields are simply like this,
Yes.
but electron will follow the field lines in a helical path, through a helical path.
Yes.
And
So
the idea is
magnetic
that
field is a certain thing like
magnetic field is upward only, sir.
no, magnetic field is along this torus.
because if it would be upward, then the plasma would have gone in a circular loop.
And the idea is magnetic field should be very, very strong, because then only this radius of gyration should be very, very small, and diffusion will be very, very small. Because if the radius of gyration is large, then particle on this field line and this field line, they will now interact with each other. So the idea is make them smaller and smaller. They should ideally be looking like this. We're going like this.
Yes.
So to generate this kind of magnetic field, what you need to have a coil. It should be generating magnetic current in this, and that will give you toroidal kind of field, which is a uniform. It should be uniform within the toroid. That is also another challenge. To get that magnetic field profile, to get that density profile, very, very challenging.
उसके लिए सर मतलब हम मैक्सवेल का कॉइल का अरेंजमेंट जो है वो यूज नहीं कर सकते। टू कॉइल के बीच में आपको हर बार ऐसा एक पॉइंट मिलता है जहाँ पर मैग्नेटिक फील्ड आइडियली यूनिफॉर्म है।
Yeah, people are trying those things, but you know there are challenges with that, especially when you do at that large scale. No, fusion reactor, they do not create radioactive waste, because there's no radioactive element involved.
Because helium is the product.
Helium is the heaviest product. So helium, hydrogens, and deuterium, tritium are interacting. Again, not radioactive. Unlike the nuclear fission, where you have to start with the uranium itself. Yes.
Also, sir, like in the ITER project, are they like doing care of the instabilities in plasma?
Yes, you have to. You should understand the instability in plasma.
पर मतलब सर अभी के लिए हमारे पास जो भी मॉडल्स है वो हम सिर्फ along the field line उसका collective motion कैसा वही देखते हैं। मतलब एक अगर इलेक्ट्रॉन जाइरेट कर रहा है तो हम सिर्फ उसके रेडियस ऑफ कर्वेचर उसके बाद।
No, in plasma there could be different kind of density, then different kind of instabilities.
Right.
Because in plasma you can have current gradient, you can have pressure gradient, you can have temperature gradient. So there's the whole class of instabilities in plasma. Current gradient driven instability, pressure driven instability, pressure gradient driven, and so on. That also depends upon your other parameters, several parameters, size of your tokamak. You should understand all of them when you make a fusion.
At the end of the day, the type of energy conversion that is used is to boil the water and take energy. So वो अभी तक
No, it's a kind of nuclear reaction.
It is
but
not like ideal water-based nuclear power.
No, but what he is saying is correct. But he is saying that eventually you will get that energy out of those particles.
Yeah, because we are trying to convert that thermal energy, right?
Yeah. So how to extract that energy is to different problem, different task. Because from the nuclear fission also you get those rods, they dump their energy through those rods, you get that water going in and you collect that energy to run the turbines and so on.
So, but is that efficient that we are using the steam power turbines, the thermal energy?
Like here, sir, we are providing this thermal energy.
Here the idea is that you will get helium, alpha particles, right? You will be getting alpha particles, which are coming at very, very high energy. So the idea is you will develop a blanket. We call it plasma blanket. So most of the energy will be absorbed by that blanket. So here it will be plasma blanket kind of. So all the energy which is carried by the alpha particle or the helium nucleus.
But that single method has not changed right from the start. So जब भी energy extract कर रहे, we are using that steam power turbines to get the thermal energy.
Yeah, eventually.
Somehow.
Yeah, they are converting into mechanical energy and finally converting the electricity.
Yeah.
Laser induced
But the thing is, as he said, the energy you give and energy you get, that ratio is less than 1. That's the problem.
Yeah.
Not less than 1, it will always be less than 1, but that is very, very small right now.
Yeah, that's for us.
this is not a what you
We
call it.
cannot harness them to full potential.
You have not reached the break-even point. Any questions from the people online? Sachin?
No, sir.
No question? Yeah, that makes teachers, instructors' life very, very easy if there are no questions. Isn't it? Let me take the attendance. Thank you then. See you tomorrow at 10:30. And tomorrow you will be having your first lecture on quantum field theory. That will be from 3:30 to 5:30. See you. Bye.